Thank you very much for the introduction. Yes, so as I just said, I don't know if everyone was there. I hope it will be pedagogical enough, but if it's not, don't hesitate to interrupt me. We can make it more informal than it is, you know, and spend longer on certain slides. So yes, I will tell you about quantum neuromorphic processors that we are building in our lab, which is at CNRS Thales. So that's some 20 kilometers south of Paris. So I originally come from quantum computing. So I will just first remind you why it is interesting to do quantum computing in case you're not used to hearing these motivations often. So the main difference between quantum systems and classical systems is that classical systems are deterministic, whereas quantum systems are probabilistic. And, you know, for a quantum system for a classical system, such as you see these planets in the solar system, their position at a given moment in time is very well defined. Whereas a position of electron, for example, that is turning around of this nucleus, proton, is not at all what we learn in school when we see this drawing. I don't know why I don't have my mouse. I'm sorry. I would like to be showing you things with my mouse on my screen, but it doesn't seem to work. No. Well, okay, I'll try to explain with words. So this drawing above where we have electron, which is on this very well-defined orbit, this is not how it works, right? This electron is kind of diluted in an area of space that we call an orbital. And it is described by a wave function, which takes non-zero values at points where this electron has a finite probability to be. So in practice, it looks more like this bottom image where you see areas of probability that goes from this purple to the orange value where we can find an electron. So why is this interesting for quantum computing? Well, it means that quantum systems, they can take few values or a very large number of values at the same time. So this is something that is very non-intuitive, and we've been trying to convince ourselves that it's true for like past century, pretty much. And there have been multiple experiments that have proven that it actually is the case. So one of the most famous experiments is this Young slit experiment that is shown on the left, where we throw some particles, and there have been particles of different sizes. In the beginning, it was electrons, but it went up to much larger molecules. And we see that actually they don't behave as particles, they behave as waves. They are kind of diluted in space. So how do we see this? Well, if you send particles on this double slit screen with a double slit, what you expect to see is two little hills behind each slit, right? Because a particle can either go through one or through other. But in practice, this is not at all what we observe. We observe this interference pattern. And this is what happens if, for instance, you have water or some other sort of waves. So this was, let's say, the first very convincing proof of this wave-like behavior of quantum particles. Okay, so now we have this property that a quantum particle can take a few different states at the same time. And then there is a very interesting property, which is called entanglement, quantum entanglement. And as you might know, last year, Alain Aspect obtained a Nobel Prize for his experiments where he observed these very strong correlations, quantum correlations, that we can't find with classical objects. So what entanglement provides that is interesting for computing is that, let's say, computing units that are very distant from each other can share information instantaneously. So people have been wondering, how to use these two features for computing for almost 40 years now. And there is a certain number of algorithms that show that actually by exploiting these two properties in a smart way, we can obtain exponential acceleration for some classical algorithms compared to some classical algorithms. So the most famous one is called Shor's algorithm, which provides exponential acceleration for a prime number factorization. And then there is Groover's algorithm, which provides quadratic acceleration for disordered database search. And a more recent one is HHL algorithm, which provides exponential acceleration for linear systems of equations. Now, the problem is that in order to implement these algorithms, we need what is called a universal quantum computer, and which would be an equivalent of a computer, of classical computers that we have today, in the sense that you could compile any algorithm using gates that you can execute on such computer. Okay, so that was the first question. Why would you do quantum computing? And the second is how can you do it? So there is a lot of different platforms. I just chose 3 here, but this is not exhaustive. I chose them because they are the most, maybe the most common ones and most advanced. Trapped ions, where we isolate single ions, which are shown here with these green balls in the ion trap. And each ion behaves as a qubit. So we select a certain transition in this ion that will be the two levels that we would use as equivalent of 0 and 1 of a qubit. Then there are superconducting qubits in the middle that we will talk more about later, because this is the system that we are using as well in our lab. Superconducting qubits have been adopted by most of industrial players in the quantum computing field for different reasons. They are on chip, which is very convenient. They can be designed on demand, in the sense you can place different parts of circuit where you want, as you fabricate the circuit yourself. And they're, well, we say macroscopic. That's kind of not completely true, because there's still there are some elements that are only a few microns or hundreds of nanometers, but there's something that you can handle with the tweezer. So it is more convenient than cold atoms or trapped ions in that sense. And the last one that I have put here, quantum dot spin qubits, where well, you have spins in a material, and then you use that spin as a qubit, and you manipulate it using gates that are printed on the surface of this material. So now, how do we compute with these systems? Well, we have equivalent of gates that you know from classical computing, but gates here are defined in a bit wider sense, because a qubit is a bit wider than a bit, meaning that it can take more than 2 values, which are 0 and 1. It can be anywhere on this sphere that you see in the bottom right. So you can imagine qubit as an arrow that is pointing anywhere on the surface of this sphere. So it's defined by these two angles, phi and theta. Theta is the angle between the state 0 and the state 1, and phi is the phase. So you can do two types of gates that will turn qubit between 0 and 1, and gates that will give it a phase. And then there are also, so these are single qubit gates where you operate a single qubit. And then there are two qubit gates where, depending on the state of one qubit, you will turn or not another qubit. Okay.
A quick question, Danijela, here. So in this 3D representation on the block sphere,
Right.
do the X and Y coordinates signify anything about the qubit? Because it seems that it's aligned either up or down, right?
X and Y coordinates, you mean, so
Yes.
so when the qubit is along X or Y, it's in a perfect superposition of 0 and 1. It's a perfectly mixed state. So if you measure it, you will have 50% probability to find it in the state 0 and 50% probability to find it in state 1.
But the X and Y component themselves, do they signify anything here? Whether it's left or right or front or rear?
So, for example, if you have a spin,
Yes.
and then it will be a perpendicular axis. If you apply a magnetic field in the perpendicular axis to the, you will have it will really be the three axis physically.
But is this phase angle, is it actually used for computational purposes, or is it just one additional degree of freedom that you don't really care about?
So it absolutely influences on the interferences between the two qubits will be completely different depending on their phase. So phase is an argument which you can use for computing. You can encode information in it.
Yeah. Thank you.
Yeah. Okay. But so this is how the let's say most common approach to quantum computing works. But the problem is, as you saw in these drawings, connectivity is mostly either in line or in plane, and we're usually only connected to the nearest neighbors. So this means quite low connectivity. And then also these two qubit gates today are still quite faulty, which means that it is quite hard. Well, it is impossible with systems that we have today to implement these quantum algorithms that I have told you about before. So what is the state of the art today? We have these, the biggest machines that we have as a humankind, not we in the lab, are the machine made by Google called Sycamore, which has 53 qubits, and the machine made by IBM last year released, which has 433 qubits. So, it's been increasing.
So Danijela, are these physical or logical qubits?
These are physical qubits.
Okay.
These are physical qubits, and last year there have been first demonstrations of error correction, where a single logical qubit was encoded in 25 physical qubits. So it's been shown that it works, but it's not as impressive as we would want it to be, and it's not sufficient in terms of how much better the logical qubit is than a single physical qubit. But yeah, this is something that people in quantum computing have been working a lot over the past 2 years, implementing error correction codes. So what is happening today is that we have these machines that are often called the noisy intermediate scale quantum devices, on which we can try to implement what is often called hybrid quantum classical computing, where we will design algorithms in such a way to do only the crucial part that can be accelerated on the quantum machine and everything else on the classical machine. And the most, let's say, common approach to do this are these parametrized quantum circuits. And I think now things will become much more familiar to you, because you will recognize a lot of things from neural networks, because they were actually inspired by them. So the way it works is that you will put layers of gates. So here I have put these big red boxes for a layer of single qubit gates that are parametrized by some angle. And then after that, there is a blue big box, which are 2 qubit gates whose main purpose is to entangle qubits between them. So after this block of one red and one blue box, we now have both superposition and entanglement in our system. And then we can do layers of that. So you see that resembles a lot the structure of a neural network. And then...
So Danijela, what is the nonlinearity part here? Is it the measurement doing the nonlinearity? What's the...
Yeah, well, there are 2 sources of nonlinearity. One is absolutely the measurement, and the other is coming from these tensor products that we have between qubits. So a quantum system, you can't consider parts of it separately. You need to consider it in a huge Hilbert space. And then as you have tensor product between each of the Hilbert spaces of each qubit, here you get the nonlinearity to the power of the degree of tensor products that you have. Okay, so then we can measure our system. We can measure each qubit and send these measurement results to a classical computer, which will then calculate gradients. So as we don't know the function that describes each of these layers, what we usually do is that we shift parameters by a little value, and then we kind of differentiate numerically using the outputs with these 2 little shifted parameters. And then you calculate the gradients, you calculate parameter updates, just as you would do with the neural network. So there have, well, I have only put two references here, but they have been much more. Today there is this IBM quantum machine that is available to community. So even if you're a theoretician or experimentalist, but you don't have your own quantum computer, you can test your ideas on this IBM machine. There is also Rigetti quantum computing in California. So there has been a certain number of implementations that are quite exciting. Actually, we do observe that we can obtain exponential number of neurons, for example, with a given number of qubits, but they are still limited, because as long as you're using qubits, the connectivity is low, and also coherence times of these qubits are not yet very good, which limits the number of layers that you can put, because all these operations take time. So at some point your system has become classical, it has completely relaxed.
Can you quickly say what you mean by coherence? Because this is also something that people say often, like decoherence is a big problem for quantum computers, but what do they actually mean?
Yes, of course. So when you when you want to describe a quantum system, you need to consider it in its whole, because there are these correlations between different components of it. So we usually describe it by what is called the density matrix, where you have these diagonal elements, which are the probabilities for each individual system, but then these off-diagonal elements tell you about correlations between different subcomponents. And these die out with time. As the quantum system interacts with the environment, the environment, we say in quantum mechanical jargon, environment observes it, it projects it, it kills its wave function. So the system becomes classical, and all of these coherences disappear. Okay. So these were parametrized quantum circuits. The other approach that has been taking that's been developing for the past few years is reservoir computing. So I suppose most of you know about it, but I will remind, however, the concept behind it. So reservoir is this neural network which uses the dynamics of a given system, such that when you send some inputs in it and you measure the reservoir at a later time, you will measure states that are more different from each other for different inputs than inputs initially were. So the idea is that different inputs will trigger very different dynamics in the reservoir. So that's how it helps you to separate the input data. So it is very interesting to implement on physical systems, because usually you have some dynamics that you can drive, and then you can measure some variables. It can be amplitude of oscillations or frequency or phase or whatever you want. And those will be the output neurons. And the second interesting thing is that you don't train anything inside of the reservoir. So when you start working with a new physical system, it's very nice to start with the reservoir, because it tells you if you have nonlinearity, if you have memory that are sufficiently good in your system so that you can use them as neurons, but you don't have to bother yet with finding a way how to train it. And then the only training that you do is done on these reservoir outputs, and it's done offline, so on your classical computer. And it's done in a single step, in the sense that, well, you have these reservoir outputs, you want to multiply them by some matrix of linear weights and obtain targets. So these weights you can quite easily find by inverting this matrix and just doing a single multiplication. So why is the reservoir interesting for our situation here? Well, we see we can't apply a lot of gates in order to obtain these layers of quantum neurons, but we can let our system evolve in time. So this will, and if we give it some interesting time evolution, this is in sort equivalent to evolving with some gates. So we use the dynamics to give depth to our neural network. Okay, so now I will come a bit to more concrete things. What do we do here in lab? So as I told you, we use superconducting circuits. Here I have just put few examples of what superconducting circuits mean in more general way, because often when you follow, news from quantum computing community, you will only hear about qubits. And often it's even just transmon qubits. But the field is much, much larger than that. There is a lot of different superconducting qubits, not just transmons that Google and IBM are using. And then also they're not only qubits, there are other elements. So here you see these lines that are resonators that can be used as some bosonic modes, so quantum oscillators. And then there are some elements that act as a memory in which we can store data. And there are some qubits as well. And you see that, we are very free to choose the length of different elements in organization on chips. So we have a lot of freedom on the circuit that we're going to design. Now, as we were discussing before the talk started, these operate in gigahertz regime, which means that in order to be in quantum regime, we need to be at below 100 millikelvin temperature. So the thing is that if you want to operate your system in quantum regime, that means that you want to isolate single photons. You want to work at the level of a single photon. But in order to be able to do that, you need the energy of your photon to be higher than thermal background. So as gigahertz is quite a low frequency compared to hundreds of terahertz that we have in optics, we need to cool down the environment such that it is colder than our photons. This is what you see at this scheme below. So room temperature corresponds to infrared. If you're working with optics, you can be quantum at room temperature. But if you work at gigahertz, you have to go down to 100 millikelvin. And to the right is the picture of our dilution refrigerator. Okay, so we don't use qubits. Spoiler alert, we use superconducting resonators. So here is a schematic of one. You see it's just a strip line, the one in the middle, that is surrounded by a ground plane. Now this is an LC oscillator. There is the inductance that is given by the length of this strip. It's a metallic cord. And there is a capacitance with the ground plane around it. So this really behaves as, a spring, a mass attached to a spring, an oscillator. And then in quantum physics, we like to describe systems using this energy operator called Hamiltonian, which here you see depends on the frequency, omega r, of this resonator that is determined by its inductance and capacitance. So by the length of the strip and the distance from the ground plane. And it depends on this number n, which is the number of photons that we inject in the system. And this is basically given by the amplitude of the microwaves that we inject. Okay. And then as our system is quantum, it doesn't have a continuity of energy states that it can take. It can only take quantized values. That's why it's called quantum, which you see here at the bottom right. So these are energy levels that are separated from each other by h bar omega, which is the energy of a single photon. So each time you add a single photon, you go to a higher energy state. Okay, but the problem is that this was all linear. You see the energy, Hamiltonian, is linear in the number of photons in the oscillators. So this is no good for neuromorphic computing. We need some nonlinearity. So how do we add a nonlinearity? Well, there is this element called Josephson junction. And this element is basically two superconducting electrodes which are separated by a very thin insulating barrier. So you see the two superconductors in red and the yellow barrier in between them. And to the right is scanning electron microscope image of one such Josephson junction. So it's the little square in the middle where there is overlap of the two electrodes where the Josephson junction is. So it happens that Josephson junction behaves as a perfect inductance, so it doesn't have any resistance attached to it. It's nonlinear, it's cosine in the phase difference between the two superconductors. So what we can do is that we fabricate such Josephson junction in the middle of our resonator. So you see at the image at the top left, I injected this little X in the resonator. This symbolizes the Josephson junction that is in the middle. And now our Hamiltonian changes. We have this additional element. Sorry? Oh, okay. I thought I heard the question. We have this additional element, which is square in the number of photons. So here is our source of nonlinearity for neuromorphic computing. So I will just show you what we have when we measure the resonance frequency of this simple system. So we just have one resonator with one Josephson junction in the middle. Here is the reflection as a function of power. So more power we put, more photons we send into the oscillator. And you see that we have this nonlinear shift to the left of the resonator frequency. All right, so now how are we going to use this system to do some reservoir computing? I will tell you about two different ways that we explored. Both are present in community, and I think it's still an open question which one will be more interesting. So we are exploring the two. The two have some advantages and disadvantages. One is what we call continuous variables, and the other is discrete variables. So continuous variables are just field quadratures. So if you're not familiar with these I and Q field quadratures, you're certainly familiar with polar ones, which are amplitude and phase. Well, here we are just in Cartesian, so we call them I and Q, in phase and quadrature, okay? And then in quantum physics, we always have these quantum fluctuations, which mean that, well, a system is never perfectly described. It's never just a point. It always has this probability to be within this circle whose diameter is equal to 1/2 of a photon. So we always have an uncertainty of 1/2 of a photon to our state, even when, as you see to the left, the state is vacuum, so there is nothing. Well, there are always some half photons even in the vacuum. And to the right, you see what happens when you inject a laser field in your system. So you will displace this vacuum with an amplitude, with at a distance, which is proportional to the square root of the number of photons. So it's called continuous variables because we can they can take a continuum set of values. So how does this look in practice in the lab? This is our sample holder on the left. You see the chip in the middle, so it's 1 centimeter by 1 centimeter. So as I told you, it's quite convenient. It's something that you can take with your tweezers. It's a full niobium. So niobium is a superconductor at 1 Kelvin. And then in the middle, so there are two oscillators. You see the shape of cross. So the vertical one is one oscillator, we call it A. The horizontal is oscillator B. And in the middle, we have inserted 4 Josephson junctions, a ring of Josephson junctions. So the way we use this system as a reservoir is that we send microwaves to each of the resonators. We send them input data, we encode it as the amplitude of the signal that we send in. And then we measure the field quadratures of each of the oscillators. So we measure 4 neurons. And in order to obtain more than 4, we do time multiplexing. So we actually measure signal for 200 nanoseconds. And then we divide it in different number of packets. And each of these packets is a different neuron.
So Danijela, so in this case, the measurement, does it destroy the inherent state of the reservoir, or you have to again create the oscillations again? Like how?
So here we don't, because we are in this semi-classical regime. We work at quite high amplitudes. So we measure continuously oscillations, and we demodulate by little packages afterwards. But in what I will show you just after, yes, measurement will be a big issue. I will show you in just a few slides with discrete variables. So here we have tested our system on this task that is a sine and square waveform classification. So it's a very common task that has been implemented with a lot of different physical systems. We have implemented it in our lab with spintronic neural networks. So, we can easily compare performance for a given number of devices and make a conclusion if there is some quantum advantage. So we send points one by one. We discretize these sine and square waves in 8 points per period. And then we send points one by one, which means we send microwaves at an amplitude that is proportional to the value of this point. And at each time, we ask the system to tell us if it belongs to a sine or to a square. So this task is interesting because it both tests if you have nonlinearity and the memory in the system. Because you see, in order to distinguish one in sine and in square, you need to remember if right before you were at 0.8 or you were at 1, right? So what we show here at the bottom, you see the prediction in orange. The target is in blue, and green is the prediction after the threshold, and actually the prediction perfectly matches the target. So we have 100% accuracy with 32 neurons, so 8, a multiplexing of 8, as we only have 4 neurons initially. So what this means is that we do have nonlinearity and memory in our system. However, we can't yet make a case if we have any quantum advantage, because we were not yet able to control the strength of coupling between our 2 oscillators. So we couldn't control the entanglement that we create between 2 oscillators. So this is something that we are still working on. And now I will tell you about this other approach where we are fully in the quantum regime. So this means that we go to very low numbers of photons in our system. And we really use the fact that its energy levels are discretized. So here I show schematically at left the 2 oscillators with their energy levels. And I will call a neuron each different state where I have a certain number of photons in each oscillator. For example, 0, 0 will be 1 neuron, 0, 1 will be a second neuron, 5, 5 will be a third neuron. And then the outputs of these neurons will be probability amplitudes to find system in this state. Because if you remember, what we were saying before. It's a quantum system. It's in a superposition of these states. So it's described by a probability to find in each of these states. So I can prepare it in this superposition with some inputs and then measure the probability to find it in each of these states, and these will be my outputs. So with just 2 oscillators, I can have up to 100 of neurons, because I can realistically occupy states between 0 and 10 photons in each oscillator. So I have 2 to the power of 10 neurons.
So Daniela,
10 to the power 2.
No, yes, 10 to the power of 2, sorry, absolutely.
So Daniela, are you still going to use the nonlinearity of the Josephson junction here, or this is like a separate?
This is separate.
Okay.
Here I'm going to use Josephson junctions to couple my oscillators, but here the nonlinearity is given by measurement. Okay, so we have only done simulations of this regime up until now. I will explain you why it's a bit harder. Well, it's a bit harder for a few reasons to do experimentally, but we're on it. So what we have done in simulations, we have tested the two benchmark tasks. First, we have done also sinus and square. And what you see here at this bottom plot is in green, the accuracy that you obtain when we measure a certain number of basis states. So with 4 neurons, this means we only measure states with 0 or 1 photon. We have, well, I don't know, 87% accuracy. Then with the 9 photons, 9 states, we only measure up to 2 photons in each oscillator. We already reach 100% with just 9 neurons. Whereas we know that with our spintronic neurons, we needed to measure, we needed to multiplex up to 25 neurons. And if you just put ReLU neurons, you need even more, because you see these are in blue. So what they call classical static are ReLU neurons in a software reservoir. Orange are spintronic neurons, and green are quantum basis states. So we were very happy to see this because, we knew that dynamics already helps a lot compared to a statical system, but we didn't know if we would have some quantum advantage. And what we understand from here is that the fact that we populate a much larger number of neurons, even though we only measure a subset of them, all these other neurons still participate to transform information. So you can separate it even though you measure a much smaller number of outputs. Second thing that I have for some reason not shown on this plot is that we have compared to a classical limit of this system where we let it decohere. So we let it evolve for a long time. We still have these discretized states, but we don't have correlations between them anymore. And we see that accuracy drops. So it really means that these quantum properties are participating to computing. And then to, understand a little bit better what are important parameters in our system, we have also tested learning on Mackey glass chaotic series prediction. And here you see error as a function of how many points in future I'm trying to predict. For 2 dissipation rates, here I call them dissipation rates. In practice, it's coupling rates of our system to the transmission lines. And most of dissipation actually goes through them. And well, without a lot of surprise, you see that if you have more dissipation, you lose memory faster. So with this red curve to the left, the error increases. Well, again, without much surprise, you see that coupling between our oscillators is very important. In the red curve, the coupling is stronger and the error is smaller. Okay, so I will try to conclude soon. First thing that I would like to say is that compared to qubits, you can see that oscillators are really interesting because we can much more efficiently populate a large number of these quantum states and make them interact. So to the left, I showed what it would look like if we wanted to entangle 8 qubits. And you see if we apply 2 qubit gates, it just takes a certain number of steps. Each of these gates is maybe 50 nanoseconds long. So you lose your coherence time by the time you have entangled them all. Whereas with oscillators, you inject signal in each of them, you prepare each of them in a superposition of states, then you let them interact, and you have already made interact all these different states. So this is why we think it's really interesting to use quantum oscillators rather than qubits. Nevertheless, there is a common problem that, it exists both for qubits and oscillators as every other quantum system, is that if we're using a reservoir here, we need to measure a certain number of outputs. And after each measurement, we have destroyed the system. So we need to prepare it again. We need to send all the inputs again, measure again, and repeat this plenty of times. So what seems to be an interesting idea is to go beyond reservoir and learn some drives that we will apply to the system such that it condenses interesting information on a smaller number of degrees of freedom, such that we only have to measure maybe 2 neurons if we have 2 output classes. So this is something that I think the direction in which I think we will have to be going in the field if we want to use these systems in an efficient way. The second direction in which I think we should be going is related to this problem of quantum measurement. So I have shown here what happens if you want to fully characterize a quantum state. So imagine you're using a quantum computer and you want to measure its output state. It's in some superposition. So it could be this state that we call a Schrödinger cat, where we have an equal superposition of 2 values. So it can be 0 and 1 of a qubit, or it can be dead and cat, which is dead and alive. And if we look at it, we will only find it in 1 position, right? We will maybe find it dead. So if you want to fully reconstruct the state, we have to prepare it a lot of times and measure it a lot of times, and then count how many times we found it dead and how many times we found it alive. And if it's 50-50, then we have an equal position, 1 over square root of 2. And if we found it more often alive, then maybe we have a square root of 3/4 of a dead alive cat and square root of 1 over 4 of dead cat. But what we could do then is replace this classical observer by a quantum neural network, such as the one that we are building, such that we input this quantum state directly through a quantum channel in the neural network. And then it projects it to 2 output values that are very different from each other, such that in a single shot measurement, we can deduce the state of the input quantum system. So this seems to me as the direction in which we should be working if we if we want to do something really useful in practice with such quantum neural networks. Okay, so that's it. Thank you for your attention. I hope I didn't completely lose you towards the end. This is our team, neuromorphic physics at CNRS Thales at left, and the little quantum team within it, with the new cryostat that we have received last week.
So just to kind of to quickly remind you what I was discussing last time. So essentially, there are two kinds of Hopfield networks on the market, right? The old Hopfield networks and the new Hopfield networks. So the old Hopfield networks can be continuous or binary, and the new Hopfield networks can be both continuous and binary. And you know, they're kind of solving the same problem, but there is a big benefit of the new Hopfield networks in the following sense, that the amount of information that you can store in the new Hopfield networks is decoupled from the dimensionality of the input space. So like you can have input space of any dimension, even like a very small dimension, and you can still store many memories. And that's what is cool about new Hopfield networks, and that's why you know, some people like them. And yeah, that's just like a reminder that in principle, although it's easier mathematically to work with binary modern Hopfield networks or dense associative memories, technically one can write down differential equations and describe the operation in terms of continuous variables. It's doable, and there is some nice mathematics behind that that you can read in the top paper, sorry, in the middle paper or the last paper. So then I also mentioned that people noticed that there's a sort.
Okay, go ahead. Yeah, sorry, I feel bad for interrupting here, but no. So this is a lot like a Boltzmann machine or a restricted Boltzmann machine, right? Where you have the hidden and the visible unit. You're doing Gibbs sampling almost between the two. Is that correct?
This architecture indeed is very similar to restricted Boltzmann machines, and the difference between this architecture and conventional RBM architecture is in how you use it and how you train it. So like restricted Boltzmann machines are typically, they're stochastic Hopfield networks, if you wish, right? So you take the energy you put inside the thermal bath, and then you do some kind of Gibbs sampling. And when you want to train them, you do contrastive divergence training, you know, something of that sort. This system is entirely deterministic. So the architecture is the same, but what the system does is very different. So you start from some high energy state and you deterministically go down to the local minimum. And that's it, right? So it's a completely deterministic system. It can be, again, continuous. It can be binary. These are technical details. And also, like, you can train it in very different ways compared to restricted Boltzmann machines. You can also train them using contrastive divergences if you wish. But for example, you can train them using backprop. You can train them using self-supervised learning. You can train them in many other ways. So like in some sense, like there is this, I would call it a dogma in the field, right? That Hopfield networks have to be trained with Hebbian learning or something like that. In principle, this is not the case. Hopfield network is an architecture, and how you train it, it's your choice. And like in the kind of, you know, most advanced applications, at the moment, we are training these new Hopfield networks using the backpropagation algorithm. And I'm not saying that that's like the you know, final statement. And at some point in the future, we might be able to come up with better training strategies. But for the moment, for practically relevant machine learning applications, backprop seems to work better than anything else that is out there. Yeah. But
I will also ask a question now directly. So we are in the projects here trying to use similar like energy minimization to solve complex like NP-hard problems, not retrieval of memory, right? So now the question that we were thinking about after after the first part of the talk was, can we not use a similar trick here, like adding a nonlinearity to also increase the capacity of that system? But I'm not sure, has work been done on that already that you know of?
I don't know. I don't know about that work, and I think it's you're asking a very, very interesting question. Indeed, as you know, I'm sure you know very well, right? Like starting from the work of Hopfield and Tank, there was a lot of attempts trying to use classical old Hopfield networks for solving various kinds of NP-complete problem, right? Like traveling salesman problems, etc., etc. And the idea there usually is that you design an energy function that minimizes the objective that you want and simultaneously penalizes the constraints that you want to satisfy. And, you know, there has been some progress on that front. And I think the kind of, you know, rough conclusion that you can solve NP-complete problems that way, but not very reliably. And it's a very interesting and completely open question to what dense associative memories can bring into that line of work. To the best of my knowledge, no one has looked into this yet. So I'm very glad that you are asking this question. It's a very interesting research question. And to the best of my knowledge, it's an open question. Yeah. Right. Okay. So I'm going to move on. So then I also brought up this relationship with large language models and transformers. And indeed, if you take a special example from the dense associative memory family, you can say that I'm going to pick the activation function for the hidden units to be a softmax. Then you reproduce the update rule for the attention. And that can have a lot of like interesting implications for state-of-the-art large-scale machine learning systems. So finally, I started discussing our own idea of using this sort of energy-based and memory-based ideas, so to speak, right, to construct better architectures for transformers that are energy-based models and also Hopfield networks. And that's one example of such an architecture, which we called energy transformer. And essentially, I roughly speaking explained to you last time how the the core computational element of this system is organized. So essentially, it's a global energy-based system which does the gradient descent at the inference time. And in order to satisfy all these constraints that are dictated by the existence of the global energy function, you have to change the internal workings of the standard transformer block in the way so that it's compatible with the energy function. And it turns out that the multi-head attention operation needs to be replaced by a slightly different operation, which we call multi-head energy attention. And the feed-forward network needs to be replaced by a feed-forward network with shared weights, which is the Hopfield network. And this Hopfield network.
So the question, is this transformation isomorphic, or you just want to get an approximation of what the standard transformer block is doing using this energy-based transformer?
Yes. So nothing here is amorphic. It's all just, creativity and hypothesis here, right? So I'm not saying that that's the only way how you can build an energy-based transformer, but here is how we build this one. We wanted to have the 4 computational elements that are used inside the transformer block. These 4 computational elements are multi-head attention, feed-forward network, skip connections, and layer normalizations. So we figure out how to embed all of these elements into the energy-based formulas. And then there were a couple of somewhat arbitrary choices, like, for example, how you plug the forward network versus the multi-head attention. Should you put them consecutively in parallel? So it's not like what I'm showing here is not the only possible solution, but it's a pretty nice solution. And in some sense, it's the sort of, how should I put it, like the most simple solution. If you want to design an energy-based system that in the forward path operates a little bit like transformer. Yeah, but I'm not claiming that that's the only possible solution. I don't know if I'm answering your question on some different question.
No, it's good.
Yeah, okay.
Dmitry, could you remind us what the GIA is and how it relates to XIA?
Right. So X is a token, And index I refers to the internal vector dimension of the token. So as you know, in transformers and in the energy transformer as well, each word in a sentence or each patch in the image is represented by a d-dimensional vector, which is called a token, right? So index I refers to this index that runs from 1 to d. Index A refers to different identities of tokens. So it runs over patches if we are doing images, or it runs over tokens in the sentence like subwords if we are doing some kind of language tokenization. So so in some sense X is a matrix of the size d by n, where d is the vector dimension of the embedding and a is the number of tokens. Now, what is G? G is Lerner normalized version of X. So essentially, everything, all these operations like Lerner, all these operations like attention and Hopfield network, they operate on the Lerner normalized tokens. So whenever we send the set of input tokens X into the energy transformer block, the first thing that we do is Lerner normalize them. And then all the energies are subsequently defined on this Lerner normalized values of G. That's why we differentiate energy with respect to G as opposed to X. If I want to be a little bit more mathematical here, I could show you these formulas. And as you can see, the energy function, it never has the variable X presented to it. It only knows about G. So like it only operates on this Lerner normalized tokens. And there are two reasons why we want to have this structure. The reason number one is that the core sort of premise of Hopfield network and any sort of meaningful energy-based model is that the energy needs to be bounded from below. And once you pass things through something like a Lerner normalization, then you automatically eliminate all kinds of infinities, right? So this is good for that purpose. But also, if we sort of get inspiration from conventional transformers, as I'm sure you know, like essentially there is a Lerner normalization step everywhere. So like multi-head attention operation is operating on the normalized tokens, and the feed-forward network is operating on the normalized tokens, etc., etc. And this diagram is a little confusing because it actually looks like a normalization step happens after attention. But remember that these blocks are stacked. So in some sense, it's a matter of convention where you put boundaries. So like the input to this multi-head attention operation comes from the layer normalization in the previous layer, if you wish. So in some sense, everything in conventional transformers and in the Hopfield transformer is operating on the normalized quantities. And that's what G is. Okay. Right. Okay. So I'm going to move on. I already explained these energies. I'm not going to go over them one more time. And I'm going to jump to like this movie that I think I sort of ended up showing last time. So essentially, bunch of images, 3 columns. The third column is the ground truth image. The first column is the initial state that is given to the energy transformer. And the middle column is the temporal evolution as the energy transformer does the computation, mapped back into the image plane. And I think like where I stopped last time, I sort of tried to emphasize that indeed the system works pretty decently. So none of these images have been used in training. These are completely new images from the test set, right? Like the system is not supposed to be exposed to these images during training time. But yet you see that the reconstructions that we're getting are quite decent. So, they're not like perfect. So if we take a look at this image, for example, I always like to emphasize this image, which has a very regular grid of bricks. You can see that right here, because some of the boundaries are completely occluded, right in the initial seed. So you can see that there is a very long brick right here, for example. There are like many more interesting aspects of the computation here. For example, you can take a look at these 2 peppers right here. And the gap between those 2 peppers was completely occluded in the initial mask. But yet you see that eventually the network does reconstruct these 2 peppers as 2 separate items as opposed to one gigantic blob of green color. So indeed, like there is some meaningful understanding of proportions of objects and what objects might look like in the real world. And all this knowledge was extracted by simply looking at a bunch of images. And that kind of looks somewhat encouraging. We technically tried testing this network on a whole bunch of tasks. And I'm going to bring one more task, which I think is very natural for this kind of network. It is a anomaly detection on graphs. Now, how should we think about this task? Think about it like this. Imagine that you have a bunch of people and each person has a bank account or, I don't know, a crypto wallet. And these bank accounts or crypto wallets, they can transact with each other. So you can represent this whole system as a gigantic graph where each node on the graph, like you can see a graph here, each node in this graph represents a bank account or a crypto wallet. And the link between the two nodes exists if there is a transaction between them. Each node on this graph can have certain attributes. For example, when the account was open, how much money is in that account, like what currencies is it operating on, etc., etc. And more importantly, it has the pattern of connectivity to which other accounts it is connected. And the majority of accounts, they are doing good things. They're like paying for lunch, they're paying for credit card bills, etc., etc. But some accounts engage in some illegal activities like money laundering, fraud, illegal gambling, etc., etc. So the question is, if we have this sort of data, and we take one node from this graph and we ask, is it a good node or a bad node? Can we solve this problem? And essentially, again, the energy transformer is a perfectly, suitable network for solving this kind of task, because essentially you can represent each node as a token. And through attention, you can look at tokens nearby. And essentially, you can let this dynamical relaxation on the energy landscape discover the labels, the binary labels for every node. So the blue guys are good guys, and the red guys are bad guys, anomalous nodes. And essentially, you can see that as dynamics that leads to the energy minimization progresses at the inference time, nodes indeed are getting labeled with their anomaly status. And it turns out that this network indeed works very well. And here you can see comparisons of the node anomaly classification task on a bunch of graphs, and some of them are fairly large. And you can also see the comparison with a bunch of benchmarks, which are mostly graph convolutional neural networks. And you can see that energy transformer performs extremely well on this task. And indeed, it's pretty much, is the state-of-the-art model for this kind of graph anomaly detection task. So there are those kinds of applications. You can obviously apply to language, and this is something that we are also playing with at the moment, but I don't have, some specific result to share with. So yeah, the conclusion here is that indeed there is this interesting architecture, which is simultaneously a transformer and a Hopfield network, and we can apply it to some interesting machine learning applications. So the next thing that I want to bring up is what we call HAMOX, which stands for Hierarchical Associative Memory User Experience. And the reason why I want to share this with you, because it's on the one hand, it's a technical tool. So it's a tool that allows you to write a code efficiently in some way. But the tool is specifically built for these kinds of energy-based networks. And I'll explain to you why in a second. So essentially, let's remember how we used to do deep learning, I don't know, 10 years ago, like in MATLAB, right? So we had like a feed-forward neural network. We had some loss function that we want to train on, I don't know, MNIST data set. And then we took this feed-forward neural network, we took the loss function, and we manually, on a piece of paper, computed the derivatives of the loss function with respect to the weights. And we, updated them in MATLAB, right? That's how things used to work before people came up with autograph. And of course, today nobody does this thing because there is an automatic differentiation tools built pretty much in any deep learning framework. And essentially, once you specify the forward pass in your network, you can just press a button and the autograph would automatically compute the derivative of the loss function with respect to weights. And this information is necessary to do backprop. Now, the cool thing about our networks is that even the forward pass in our networks is actually a gradient of the energy function. So wouldn't it be cool to also use the utility of autograph to eliminate the programming of the forward pass as well? And that's what HAMux does for you. So essentially, you don't have to write even the forward pass for the network. You just need to tell which layers you have and how these layers are connected. And that information is sufficient. And then you just press a button and the autograph can automatically compute the forward pass for you. And then if you want to train this network, it will compute the backward pass in backprop as well. So that's a convenient tool. And there is one extra step in HAMux compared to what I have just described. And that step is the following, that it turns out that even the energy function is not the most fundamental mathematical object in these networks, but the real fundamental object is the Lagrangian for every layer. And essentially, and I didn't really explain this because it's a subject of another sort of an hour-long seminar, how to engineer these networks using Lagrangian functions, but I did point out to the paper where we developed this formalism. So one paper is this one from iClair 2021, and the second paper is on archive also from 2021. But essentially what HAMux does is the following. You specify the layers, you specify the connectivity between those layers, and you specify the Lagrangian for every layer. And then you press a button, and then HAMux does the rest of the work for you. So it's just like a kind of, a very nice software engineering tool and software engineering abstraction, if you will, that allows you to efficiently program these energy-based Hopfield networks. So if you're interested, please take a look at the GitHub repo. It's completely open source, and it's an evolving project, but none of the stuff that I told you about in the energy transformer, for example, would have been possible without HAMux. So it's a very sort of, convenient tool that makes programming these systems much, much, much easier than without HAMux. Okay, so, and I think that's pretty much it. I'm gonna jump to my conclusions. So the first thing that I want to say again is that the sort of long-standing problem regarding Hopfield networks, how can you put a lot of memories given a fixed dimensionality of the feature space is solved. So in these new versions of the Hopfield networks, pretty much the amount of information that you store in them is completely independent. It can be made independent from the dimensionality of the feature space. So you have some freedom. They can be continuous, they can be binary. It's your choice. Again, there are networks of both natures. They can have many hidden layers. They can have hierarchical representation. So essentially, it's not just two layers like hidden neurons and then that talk to the feature neurons. You can have many hidden layers, and you can put them on top of each other, and that would be a perfectly viable Hopfield network, and you can work with it. And sort of the most important, I think, conclusion, and the most high-level conclusion is that I genuinely believe that in this sort of modern world where transformers are everywhere, this sort of theoretical prism of thinking about transformers through the lens of associative memory and energy-based models can open up both new architectures that we are exploring and some other people are exploring as well, but also can help us understand what the pre-trained transformers are doing. So I think at the very least, it's a very nice theoretical tool that allows us to think about transformers from a slightly different perspective. So yeah, that's pretty much all that I wanted to share with you. So it didn't really take too much time today, but
yeah, thanks a lot.
So Dmitry, a question for you. So you mentioned that you train these networks using backprop. And so you have a global energy and you have a local energy. Am I correct in understanding that? Like, and how do you manage backprop between the two? Is it a simple addition of all the local energies to?
So here is how it works. I'm just trying to see. 1 sec. So let me sort of go back to this slide, right? So our networks have two functions that are being minimized. The first function is the energy, and the energy is being minimized as a function of states. So X is the state vector, and let's dedicate another letter. Let's call it W for the weights, right? So like whenever I'm talking about minimization of the energy, I'm only minimizing energy with respect to the states, and weights are fixed during that pass. That's the forward pass. Now, of course, we want to train weights, right? And what you do is the following. You take some initial state, you take a data point, for example, mist image. You occlude something on that image, right? You evolve that image according to this energy minimization until it hits the fixed point. Then you take the fixed point, and you say, how is that evolved image different from the ground truth image that I want to compare with, right? So you can take that fixed point, you can subtract from it the ground truth image, and you can form a mean square error function, the standard loss, like everyone is using mean square errors in training deep neural networks, right? So now we have two functions. One is the energy function, which is a function of X. And then the other function is the loss function, let's call it L. And L is a function of W. So, and that's what it means. So in the forward pass, we minimize energy with respect to states. And in the backward pass, we minimize the loss, the L function, with respect to weights.
So do both the processes, can it go hand in hand, or do you have to make one stop and then let the other take over?
I mean, in practice, like we train with mini batches, right? So you take like a batch of images, you give them the weights are fixed, right? So you take that batch, you pass it to the network, you go to the fixed point, to one fixed point for every image. Then you collect the fixed points from for all the elements of the mini batch, and then you define the loss function. And then you take the derivative of the loss function with respect to weights. So you update the weights once per mini batch, and you update images throughout the whole evolution on the energy descent.
So does that mean you cannot have an online version of this algorithm? We could. I mean, there's nothing that would prevent us from doing things online. You can take a mini batch size to be equal to 1. And everything would be the same. Like this system are completely like agnostic about that aspect. They can be, you can train full batch, you can do mini batches, you can do online. They can do all three options.
So it sounds like the equilibrium propagation that you got two bases. Evaluate the, without evaluate the fixed point that.
Yeah, because what happens if you don't let the network settle down to the fixed point and you start updating the weights?
Yes. And in practice, of course, it never settles down to fixed point, right? Because you're always like 10 to minus 6 away from the fixed point. So like that's you have to live with that. So there is some finite precision, and you need to get close to the fixed point, but then you do the backward path. So speaking about equilibrium propagation, great idea. I've never tried training these networks with equilibrium prop. Indeed, they're perfect for equilibrium propagation, at least from the high level. But my understanding, although I'm not an expert on equilibrium propagation, that equilibrium propagation is in general very capricious tool, and like people don't really have not been able to demonstrate that it works very well. But having said this, maybe it doesn't work for some other architectures, but maybe for these architectures it will. I have no idea. It's a great question. If any of you are interested, I would be very interested in thinking about this question.
And also, Oh, sorry, there's a question in the chat.
Question in the chat. I
Chat,
can.
Yeah.
Could you explain how Hopfield network takes care of the attention mechanism? Right.
Network.
So I'm kind of a little bit unsure what you mean by that, but let me try. So let's think about images again for simplicity, right? So what attention does is the following: it mixes different tokens. So for example, I take this image, I split it into individual patches, and some of the patches are revealed and some of the patches are gray. We don't know what they are. So that's the initial state. Now, this is the Hopfield network for the attention. So like the conventional attention, it has queries and it has keys. For reasons of compatibility with the energy function, it does not have values. So the values are actually constructed from keys and queries in this step. But essentially, think about it like this. So in order for, like, let's say that I'm the gray patch, and I want to know whom should I become, right? So what I need to do, I need to ask other patches nearby or farther away who they are. So for example, I see that there is a patch here next to me, which is green. So I send a query to that patch, and the patch tells me that the key for that patch is green. So I get some information back to my patch. And the way how this energy is defined is the following: when all the queries are aligned with the keys of other patches. Because if the queries are aligned with the keys, then this term becomes big. And this term becomes big, then the derivative of this energy function, which is the softmax, becomes very peaky. So I don't know if I've answered your question again or some other question that I have created myself, but that's roughly speaking.
Mm-hmm. I have a couple of questions.
Uh-huh.
So what is R in EHN?
Right. What is R? R is an activation function. So think about R as a rectified linear unit.
I see. So it is an on-off type function?
It's equal to 0 for negative values and it is linearly growing for positive values. So its function looks like this.
Okay. The second thing is you said some about loss function.
Yes.
Your backward propagation. What is the physical basis of that loss function? Is it like a dissipation term or what exactly is it?
I would say it's just a mean squared error between...
So it's just a numerical minimizing variation?
Yeah, yes. So essentially, like you have the ground truth, the image that you want to obtain at the fixed point. And you have the actual result that the network has obtained so far, given the current set of weights at the fixed point. And you want to move them closer to each other, right?
Mm-hmm.
So it's just like, like mean squared error, like we do in like physics 101 physics labs, right? We like measure like a quantity 10 times, and then we compute the means like this mean and the standard deviation.
Okay, okay. Related to that, you mentioned in the passing about Lagrangian.
Yes.
So the energy is still this energy term that you see in EHN, correct?
Well, any of these energies can be derived from the Lagrangian.
That I agree. But my question is, why do you need to switch to Lagrangian if you already have the energy?
Yes. Yes, interesting question indeed, it's a great question because I did not explain this at all. And so let me first of all briefly explain what I call the Lagrangian here. So all these nonlinear equations have some activation functions like f, g, and like think about them like f can be a softmax, for example, and g can be like a linear function or a rectified linear unit. Now, it turns out that it is convenient to integrate those functions up one level. And the Lagrangian is defined as the integral of those activation functions. And you would think that it's just a tautology, right? I could have defined things through activation function, and I said, okay, I'm going to define it through the integral of that activation function. Who cares? But it turns out that it's a very smart kind of, way of thinking about the system for the following reason. Because once you define everything in terms of these auxiliary functions that we have called Lagrangians, and I'll explain why in a moment, you can compute the energies for these whole systems as Legendre transformed of those Lagrangians. And of course, like for anyone with physics background who knows how to kind of, do things in classical mechanics, we have Lagrangian systems, and then we do Legendre transform, we get the energy. So the same thing here. And that's why we call that auxiliary function the Lagrangian. But I also want to emphasize that that analogy stops here. So we don't have any form of Euler-Lagrange equations in this system. For example, we don't have the general structure of Lagrangian mechanics. So the only reason why we picked that word is because the energy is related to those auxiliary functions through the Legendre transform.
Okay. The VIs are the nodes, and the
VIs are the internal states of the neurons. And GIs are the firing rates, if you wish. They are activation functions acting on those neurons.
Okay, so they will be like a heavy side function or something.
Yeah, they could be like a heavy side function. Correct. But let me also say one more thing, because again, I should have said this, but I didn't. So it's when you are working with neuron-wise activation functions like rectified linear units or I don't know, sigmoids or hyperbolic tangents, it's almost tautological to work in terms of activation functions or in terms of Lagrangians. Things get way more interesting when your activation functions start mixing activities of many neurons, like in machine learning. In machine learning, we have softmaxes, we have layer normalizations, etc. And it is precisely in that domain, when you start dealing with these more complex objects, it is infinitely easier to think about your system in terms of the Lagrangians compared to the activation functions.
Okay, yeah. And the H, sorry, the last question is, what is the H?
What is the H? Which H?
H mu. H mu.
H mu. Right. So yes, let me talk a little bit about these equations. And again, if you want to understand them better, please take a look at this.
Yeah, I will take a look.
But let me explain what these variables are. So essentially, here in this network, you have two groups of neurons. The blue guys, let's call them feature neurons, and the green guys, let's call them hidden neurons. So each of those two groups, so each of these neurons, both blue and green, have two variables associated with them. The internal state, which is called V and G for the feature neurons. V is internal state, G is the activation function acting on the internal state. So think about V as a current and G as a sigmoid of that current, for example. Or biologically, you can think about G as the firing rate. And for the hidden neurons, the corresponding two variables, the internal state would be H mu, and the activation function would be F mu. And they are enumerated using different indices because they are different neurons, right? So like these neurons are enumerated using index I, which is the Latin index, and the hidden neurons are enumerated using Greek index mu. But apart from that, these these two groups of neurons are very symmetric. So let's take a look at the first equation. The first equation has some input current, it has the decay term, and it has the effect of other neurons. So essentially, psi I mu is the synaptic strength, right? You collect all the activities, all the firing rates from the green neurons with the firing rates of mu's, you multiply them by a weight, and that's the input to your input neuron. And the same thing for H mu's. Now you look at all the visible neurons or feature neurons. Each of those feature neurons has an activation function GI, the firing rate. You multiply them by a set of weights, and you have decay term, and this is your time derivative. So it's kind of like a firing rate model.
Okay, thank you.
And let me ask you, so you mentioned, right? So this is like a restricted Boltzmann machine, except without the stochastic nature. And so in your experience, or so is it advantageous to have continuous analog dynamics as opposed to stochastic variables? And I'm asking partially because Boltzmann machines typically are less prone to, say, QiNS local minima versus Hopfield network, at least in the classical Hopfield nets, right? And that's part of the reason why Boltzmann machines were introduced, right? So that the noise is introduced into them.
Right.
Is able to overcome local minima.
Yeah. So I'm going to give you a high-level answer to that question first, and then I'm going to go kind of deeper into more granularity, so to speak. So the high-level answer is the following. Historically, Hopfield networks were first. Restricted Boltzmann machines came out after Hopfield networks. Now we are sort of, we have another iteration, right? We have new Hopfield networks. They have slightly better properties, but we don't have yet restricted Boltzmann machines built on top of them. So I think like eventually like there will be some papers and some like people who start thinking about this, and eventually there will be some interesting applications of stochasticity in these new systems. We just haven't, you know, like these results are pretty new, as you can probably tell from the dates, and the topic is not like super hot. So like it's a niche topic, right? So there is some community who is interested in this, but it's not like it's the mainstream thing that everyone at Neurops is working on. So, and from that perspective, I've only seen a handful of papers that investigated the properties of these systems in the stochastic setting. I'm not saying that it's, you know, there's nothing interesting there. I think there's a lot of interesting phenomena there, but they just have not been explored yet, right? So you can certainly build restricted Boltzmann machines or unrestricted Boltzmann machines using these new Hopfield networks as well. And I think it's a very interesting direction of research. Now, sort of coming back to the question, is there anything beneficial in deterministic dynamics versus stochastic dynamics? Again, yes and no. In some sense, the cool thing about deterministic dynamics is that you can train it with backprop, right? So it's like, it's a dynamical system. It converges to the fixed point. So you can wait until it converges, and then you can do backprop through time and adjust the weights. So that's something that's that we are currently using. And from that perspective, it's indeed, it provides a slightly different way of training RBMs. And the reason why people have not used that method for conventional RBMs built on top of old Hopfield networks is because old Hopfield networks, they have way more local minima than memories. So like the majority of the local minima in those systems, they correspond to spin glass states. The cool thing about new Hopfield networks is that the spin glass phase is suppressed in them. It occupies a very small amount of space for reasonable amounts of hidden neurons and feature neurons. And for that reason, you can actually train them with backprop in the way how I described.
So that's something I actually missed here. So you're saying that these continuous modern Hopfield networks are actually those extension to the classical Hopfield nets that no longer have that constraint on the capacity being just 0.14 times the number of nodes. Right. Because now you have this, now you have both the F and the G activations.
Yes, great question. So, so if you measure the capacity of the system as a function of the total number of neurons, both green and blue, then the capacity would still be linear. It would be, the number of memories would be, could be a very complicated and very aggressively growing function of the dimensionality of the number of blue guys, but it will still be linear in the number of green guys in this simple architecture. Yes. Right? So, but the cool thing is that often you are in situations, especially in machine learning, and for that matter, in the biological brain, when the number of hidden neurons can be big and the number of blue guys is fixed. It's the dimensionality of your image or your tokens or whatever. And in that regime, you simply, like the problem of the old Hopfield network, it's not so much that the capacity was low, but it's more that it was completely determined by the dimensionality of the feature space. And now it is not. So now it is decoupled from that, and that's what makes these systems more convenient to work with.
So is it correct to state then that those green units, those internal units, correspond to those nonlinear projection that you have in a few slides back?
Correct. They do. Yes. Yes, indeed.
And do you allow for lateral connections here between the neurons?
You could. You could. The formalism is completely like, again, this simple model does not allow that. But if you look at my paper from 2021, for example, where is it? This one. It's called hierarchical associative memory. Over there, you can have any connections that you want. You can have connections, you can have like 10 layers stacked on top of each other, and you can connect them in very, very sophisticated way. And that would be totally perfectly viable Hopfield network.
But what is the condition on which you can always derive an energy function? Is there a restriction on the connectivity?
Yes, the weights need to be somewhat symmetric. And what this means is the following, that you see, like, for example, in this simple network, the matrix of weights that projects from the blue guys to the red guys is exactly the same as the matrix of reverse projections. So if you introduce lateral connections, for example, I can take the green guys, I can induce another all-to-all connectivity within this layer. That matrix needs to be symmetric. So if you satisfy those constraints, you can write down the energy. It has a Lagrange and it has everything. And like, if you indeed take a look at this hierarchical associative memory paper, you can it's explained how to do it.
But then you cannot have oscillations then.
You cannot have oscillations, exactly. And that's again the sort of the main premise of Hopfield networks. A good Hopfield network should only have fixed points, right?
But that may not be entirely true, right? Because sometimes actually limit cycles may be beneficial in some of the.
Well, it could be. Yes, I agree with you. But again, kind of, in that sense, I'm restricting myself. What I'm trying to do here is to get rid of all the possible limit cycles, chaotic behavior, strange attractors, etc., etc. I want only fixed points.
You want to build an associative memory, right? Yeah.
Excuse me?
You want to build an associative memory.
Yeah, I want to build an associative memory. I want to associate the input with the output. Having said this, let me point out something to you. In one of the architectures that I have extensively discussed today, which is the energy transformer, there is actually a limit cycle, and it comes from a symmetry that exists in the system. Think about this function G. So the function G here is a layer normalization step. And how you compute a layer normalization step is the following. You take X, you subtract the mean of X, and then you divide by the standard deviation. Now, when you subtract mean from the X, it means that you can shift X by a constant, and it would never change G. Because you divide X minus X mean by the standard deviation, it also means that you can multiply X by a constant, and this would not change G either. So there are these two zero modes, these two symmetries that you can shift around, you can shift X, but this would not affect the energy. And the existence of these two zero modes results in the limit cycles that you kind of described, right? That essentially, like, the network collapses to a certain manifold in the space of X's, and then it does something on that manifold. So again, like, the question of zero modes is always subtle when we deal with Hopfield networks, and that needs to be carefully analyzed for each architecture of your choice. So sometimes there are those, zero modes. Sometimes there are none. In the energy transformer, there are zero modes, and there are exactly two zero modes.
I wanted to ask a simple question because I'm not sure I quite understood that part. So in the traditional Hopfield network, there is a very straightforward algorithm how you imprint the memories in the network, right? By just taking ordered products. In this new form with the nonlinearities, how did you again construct it so that you know in advance which fixed points you will have in the network? Like, how
Right. Right. And again, let me partly start again from answering your question from a high level. And the first thing that I want to say again, which I already said, but I want to re-emphasize it. People often sort of confuse two different questions. The question number one, what is the architecture? And the question number two, how you train this architecture. So for me, like these are two completely different questions. And by and large, most of the stuff that I have discussed today is about the first question, what is the architecture? And I, by and large, did not talk about how we train those things. Now, now I'm going one level of granularity closer to the actual question that you asked. You can ask me, given these new Hopfield networks, can you train them in the old way, like Hebbian learning? You give me like certain patterns, I'm just going to embed them into the memory without any backprop, without anything. Just, you know, outer product or something like that. Can you do it with the new Hopfield networks or not? The answer is yes, you can. You can do it, and it's very straightforward to do it pretty much in any of the models that I have described to you. You have that capability, but you also have a different capability, which you have both in the old Hopfield networks and in the new Hopfield networks, to train them using some other algorithm, like backprop through time, maybe contrastive divergence, whatever, right? So it's a kind of, you know, it's a question about how you train those systems, and you can train those systems in the way how you want them to train. And actually, let me go back to my first slide where I have literally done just that. So like in this slide, right, I literally took a handful of images and I embedded them in the Hopfield network without training, no backprop, nothing. Just, you know, you give me the images, I, you know, say my weights are equal to the pixel-wise intensities of those images. And you can see that it works. It's a modern Hopfield network, so it does have like much more favorable capacity compared to the old Hopfield networks, but it's trained using Hebbian learning, if you wish.
Okay, cool. And a quick follow-up, this is so I very vaguely remember some like 2 or 3 years ago, I don't know, I was listening to a talk by, I forgot where they were from, but they were talking about implicit layers. I think that's what they called it. And so what I think what they did is they used the implicit function theorem to do what you want to do, like to shift around the fixed points, but not through like backpropagating through time entirely, but to basically use the like the fixed point equation to directly change the position of the fixed point. To like, I'm not sure exactly how to paraphrase this, but like I'm not sure if you're aware of this like implicit.
I'm aware. I understand you. I understand what you mean. Yes, yes. Thank you for this question. Fantastic question. Indeed, these networks are perfect for those systems. And again, you know, this idea is actually quite old. Like in the old days, this used to be called recurrent backpropagation. Some people call it Almeida-Pineda algorithm because it was introduced by Almeida and Pineda independently, more or less like around early 90s. In the modern reincarnation of this idea, it has names, something like neuroordinary differential equations. Sometimes people call it deep equilibrium models. Sometimes people call it implicit layers. Perfect idea. It's like all those methods should work for our systems. We are playing with this. We have not been able to. I don't have any results to show to you. But indeed, you can write an implicit equation directly on the fixed point without doing unfolding in time and backpropagating through the unfolding procedure, like we're doing backprop through time. And that should save some compute time during training. Yeah. So, I mean, again, it's a very interesting direction, and not that many people are looking into this. So if you're interested to do something along those lines, I think it would be incredibly timely and very interesting, at least for me. So I don't know how recurrent backprop or implicit layers, you know, interact with these architectures, and I don't think anybody does.
Okay, let me ask you one question.
Please, yes.
Can you go back to the continuous like Hopfield model? Next. Oh yeah, that one. Oh, sorry.
This one?
Yeah.
Okay.
Like the dynamics, right? You have two, like dynamic equations which are cross-coupled, right? But they are actually low-pass filters, right? So
they are what? Sorry.
Low-pass filters. So take a look at the right-hand side. You have decay and the source, right? Both of them. And that means, but actually, the fixed point is very obvious. You will actually have to solve that differential equation. The fixed point, I mean, the steady state is just simply right. So, for example, take a look at the first equation, the fixed point, or if you think about just null lines of these two dynamics, right? And VI equals blah, blah, blah. And HU equals blah, blah, blah. So my question is, why do you really care that as dynamics? Because the fixed point is so obvious, right? And this is my first question. And the second question is, if you really consider that as dynamic system, you got two time constant, right? Tau F and tau H, right? So it can be really, really tricky. So it depends on the choice of these two time constant. If you make them like more or less the same, I'm pretty sure that it never converges, right? So if you make them pretty, different from each other, then of course then you can use, this kind of like quasi-static, approximation, so that you don't need to solve the whole, this differential equation. So simply my question is, there may be a like easy way to handle it, but nevertheless you take that kind of, this complicated approach. This is my question.
Yeah. Great question. And so let me first slightly disagree with you on your first question. So indeed, let's take a look at these equations, like literally as they are written. And imagine that Gi and F mu are some complicated nonlinear functions, right? As they are like in reality.
Right.
So then you can do something along the lines that you have said. You can, for example, say, imagine that my tau H is way, way, way smaller than tau F. So like the second equation equilibrates way faster than the first one. If that is the case, then indeed you can solve it explicitly. You can say that H mu is equal to G mu I Gi, sum over I, right? And you can take that thing and you can plug it into the F mu, which is a function of H mu. But then you will get like a very, very sophisticated nonlinearity right here. And of course, you can probably solve it numerically. You can find that fixed points. And there are like, numerical ODE solvers that use like Runge-Kutta methods, etc. So you can find that fixed point. But then if your goal is to train the size, to train the weights, you need to use something what the previous person who asked the questions, like you need to use some idea of implicit layers or recurrent backprop to find those weights. And that's a meaningful thing to do. I'm not saying that it's not meaningful, but kind of, the zero fodder approach to that problem would be to reiterate them, to iterate these equations in time and do a backprop through time. So I'm not sure that by just simply, and notice that although the second equation is very easy to integrate out, like this variable H, once you do that, the remaining equation is very nonlinear equation, right? So it can have many fixed points depending on the initial conditions. And you need to somehow like find all those fixed points. Even like finding all those fixed points, it's already a complicated problem. And the number of those fixed points, it can be very big. It can be exponentially big in the number of NF, in the number of feature neurons. So it's not like a trivial problem to solve these equations at the fixed point, right?
Yeah.
Do you agree with me, or again, I could have distorted your question?
I agree with you. I think it depends on the time constant you choose. Also the like. Yeah, I understand that these are like nonlinear equations, so you have to solve them, like iteration for sure, right?
Yeah.
So I think that can be a good way. You know, I don't know. I've heard about that model for the first time in my life. So
It depends whether you're a DSP person or neuromorphic engineer, right? So you like analog, fixed time dynamics, or you like iteration, fixed sampling, so
I'm doing digital, so yes, I like iteration.
But also notice that indeed the fixed points, they do not depend on those time constants, right? So, and neither does the energy. So the energy function, which defines the fixed points, it's completely independent of the kinetics. So it only depends on parameters size and the nonlinearities, the activation functions f and g, but it's completely agnostic about tau f and tau h. And what dynamics does, it indeed kind of, you know, it describes the trajectory, how you go to those fixed points. And this trajectory can be extraordinarily complicated depending on what tau f and tau h you pick. And I completely agree with you on that. And the fixed points, they do not know about this.
You know, what I mean is, you have to think about the left-hand side because, you know, that, you know, take a look at the first and second equation. Like what
except that initial conditions towards for
oh yeah, right. Yeah, it's very complicated. Yes. Okay, yeah. Gotcha.
And that's for retrieval. Let's say you have the parrot or
Yeah, but also, like, you know, like, again, if you take a look at this paper on hierarchical associative memory, I even like dedicate a section in that paper by analyzing what I call an adiabatic limit of those equations. And adiabatic limit precisely corresponds to the situation when the time constant in the top layer, in the very, very highest layer of the network is very small. And then you can slightly simplify things. You can indeed integrate out this top equation, this top layer entirely. But then, like, still the remaining system is very nonlinear and very complex system, which has a bunch of fixed points.
Right. Yeah. Good. Thanks.
Yeah. One more question about the energy transformer.
We have more questions online.
Yeah, there's more questions online. So.
Okay.
Can you go to the slide where you talk about the energy transformer?
Yes. So let me read the question. How are keys and queries generated in the energy attention term? Are they calculated from the tokens through a feed-forward network, like in the standard transformer? Yes, they are. And let me go to that slide and we can talk about this. Yes. So, right. So essentially, both keys and queries are calculated in the most standard way, like how you calculate them from attention zone unit paper, right? So you take x's. X has so again, this formula is a little bit more complicated than it should be because it has many heads. So index h here corresponds to different heads of attention. Indices b, c, and b and c correspond to the token numbers. And index alpha corresponds to the internal dimension in the attention operation, right? So, but essentially both key matrix K and matrix Q is computed by taking the dot product of the layer normalized token, which is denoted by G, and multiplying it by a linear by a matrix. And that matrix is learnable. So there is WQ and WK.
Okay, got it. So the whole field network dynamics is used to minimize both the attention energy and the standard whole field net energy.
Exactly.
My follow-up question would be, is it necessary to have the attention energy separated from the whole field network energy? Because from my understanding, the attention is basically a communication method that lets myself to know like what's surrounding me, what information do I have the neighbor near me. But whole field network actually does the same thing because that's
like this whole field network does. This whole field network operates on a per token basis. It never mixes tokens.
Oh.
So it's literally like an analog of a feed-forward network in the conventional transformer block. It takes the token. You see, like I just literally add the energies of all of the tokens. I sum with respect to B, and the contribution is additive. So there is no any interaction between the tokens. So essentially, it's a Hopfield network that operates on a per token basis. And the only way how the token located here can get some information from a token nearby is through the attention. So like it is this energy that drives the communication between the tokens. And it is this energy that drives the sort of evolution of tokens as in the, like, as if that token was alone in the universe.
Do you think it's possible to explore ways to, get rid of the attention and embed this communication scheme in the whole field network? I mean, in the future direction, as a future direction.
Possibly, yeah. I mean, indeed, like take this framework, throw out energy attention, and write a better energy attention. And if you do it right, and if your system works better, then everyone is going to be using it. So it's a completely like, it's a very interesting research question, how to engineer these systems. What is the right energy?
Yep.
We have designed these specific energies, E attention and E Hopfield network, to make it as close to the conventional transformer as possible. And because we kind of know empirically that conventional transformers work very well. But no one ever claimed that transformer is the optimal architecture, right?
Yeah.
So there could be better architectures that have better communication properties between the tokens, that may perhaps have better trainability properties under backprop through time, or under recurrent backprop, or maybe under Hebbian learning, or whatever. So it's a completely open field here. It's a very interesting question how to write down better, routing schemes between tokens.
Yes, exactly. Thanks.
Completely agree. Yeah, if you come up with some good idea, make sure to send me an email.
Okay, if there are any more questions, thanks, Dmitry. Thank you.
Thank you for the invitation. It was fun, chatting with you all.
Okay, thank you.